If I asked you to draw a bond line structure of cyclobutane, you would draw something that looks like what I've drawn here, basically a square. Well, what's wrong with this? If each of these single bonds is tetrahedral, or wants to be tetrahedral, and have a bond angle of 109.5 degrees, in this case the bond angles are about 90 degrees. This adds a lot of what we call angle strain. Basically, we're forcing a tetrahedral sp3 carbon into a shape where the angles are compressed. This adds a lot of energy to the bonds. The problem with considering angle strain as the sole contributor, though, is that cyclic alkanes aren't flat. So let's take these two bottom carbons, beginning rotating them up towards you. It'll look a little bit like this. You can already see this is not a perfect square. It's a little bit distorted. We rotate it all the way. You can see that these two carbon atoms are not aligned directly like you would expect in a flat molecule. Cyclic alkanes are not flat. What they do is they pucker. The bond angles change a little bit so that they can get closer to the ideal angle of 109.5 degrees and lower other sources of strain. So let's add the hydrogens into this cyclobutane and compare. In this case, we can take a look at the bond angles. They're actually 88 degrees if you measured them. There are a couple of problems with this, though. First, these hydrogen atoms are eclipsing. Notice they're all kind of in the same place. This adds what we call torsional strain. These hydrogen atoms don't want to be close to each other, so they want to be moving away. But at the same time, the farther they move away, the farther this distorts this bond angle. So this puckered shape is basically the way cyclobutane method of minimizing and balancing these two energies. Cyclobutane, because there is so much angle strain and because there is this torsional strain, is less stable than some other cyclic alkanes. If we did cyclopropane, a triangle, the bond angles get even worse, and there's even more strain associated with making that molecule. So let's take a look at a larger ring, cyclopentane. Again, if we drew this as a bond line structure, you'd see this pentagon type shape. The bond angles in a pentagon are actually about 108 degrees, which is close to the 109.5 degrees that a tetrahedral compound wants to adopt. Begin rotating it towards you, you could see that already there's some distortion right here. If we move it all the way, we get a puckered shape as well. Why is there this puckered shape? Let's add in the hydrogen atoms. Again, you can see that there is eclipsing of some of the hydrogen atoms. And when these hydrogen atoms are eclipsed, there's additional torsional strain, even though the bond angles are roughly 109.5 degrees, or at least they're close. So cyclopentane is more stable than cyclobutane is because the bond angles aren't nearly as bad, but we still have this eclipsing strain. The most stable cyclic alkane is cyclohexane. And again, if we looked at this as if this were flat, these bond angles are 120 degrees. That's really far away from 109.5 degrees. So let's rotate towards us a little bit and all the way, and we get this conformation. If we add in the hydrogen atoms, first thing you should notice is they're not eclipsing anymore. This hydrogen atom is pointing away from this hydrogen atom. This hydrogen atom is pointing away from this hydrogen atom. So we don't have the eclipsing strain from the hydrogen atoms. The other thing you should recognize is we have this nice tetrahedral shape. If you consider the Newman projections we were drawing before, they look very similar, especially if we make a little circle here. We align these. So cyclohexane in nature is basically perfect bond angles. There's no angle strain. All the bond angles are 109.5 degrees, and there's no torsional strain from eclipsing hydrogen atoms. Cyclohexane's typical conformation, like I said, is a chair. Well, the first thing you should notice is that these bonds here and here are parallel. These bonds here and here are parallel. And these bonds here and here are parallel. So if you look at the shape that I've just drawn, you can mimic that shape. First, we're going to draw this bond and this bond. Next, we will draw this bond and this bond. And then we'll just connect everything. There's our chair conformation. Notice it's not as nice as the computer image, but it works. Now if we want to add in the hydrogens, there are two types of hydrogen atoms we can add. They're called axial and equatorial. The axial hydrogens are the easiest to add. Basically, wherever two bonds, say this bond and this bond, come to a point right here at this vertex, we're going to have hydrogen straight down because the vertex is pointing down. If we move here, these two are pointing directly up, down, behind that bond, up here, and down here. This gets easier with practice. You have to be able to practice this so that you can draw them more quickly, and so you can draw them without a template like this. The hydrogens we've drawn so far are axial. So we can label all of these A. These are the easiest to draw. The other type of hydrogen that we need to draw is called an equatorial hydrogen. These come off to the side. If we look at our picture, this is an equatorial hydrogen. This is an equatorial hydrogen. How do we get the right bond angles? One way to do that, say if we're looking at this bottom left carbon again, kind of pretend that that back bond doesn't exist. If we do that, we have 2/3 of the bond angles that we see in a Newman projection. We just add in the third one right here. If we look at the bond behind it right here, again, ignore the bond coming off to the front right there. Do the same thing all the way across. This is very easy to do on the outside carbons, so I'm going to finish the other outside carbons. Again, if you're not sure how to do this, take a look and practice a little bit. The middle carbons are a little bit harder. You should notice that this bond angle here and this bond angle are parallel to each other, and the hydrogen coming off here, the equatorial hydrogen, is also going to have that same angle. Same thing with this other one. It's going to be right here. So what you should notice if we look at the axial hydrogens is they alternate up and down. Up, down, up, down, up, down. The same thing occurs for the equatorial hydrogens. Up, down, up, down, up, down. If they're not alternating, then you've drawn it incorrectly. The other thing about chair conformations is that they can flip. So let's draw that original chair conformation we had before. 2 lines, 2 lines, and then connect. This is not as pretty as the last one. We could do the same thing with a chair flip. So instead of drawing the first 2 lines down and to the left, let's draw the first 2 down and to the right. Add a line, and connect. What is different about these two? It's the same basic shape, but this bond here ends up shifting and flipping up. So when we have a transition between a chair flip, if this was carbon 1 originally, carbon 1 is now here in the middle. If this is carbon 2, that's now here. Carbon 3, which was down, is now pointing up. And go around and number all 6 of them. Notice the carbon atoms flip during a change in a chair conformation, but the other thing that flips is also the placement of the atoms. So let's draw the hydrogen atom here, the axial hydrogen atom. Notice that's pointing down. As we do the chair flip, the hydrogen pointing down is now equatorial. These are the same hydrogen. They've just changed their relative position because the carbon has changed as well. If we take a look at the equatorial hydrogen, which is pointing up, it now switches to the axial position, pointing up. So if we put a little star here, this is the same hydrogen. If you want practice, go back, draw some chair conformations, do a flip. You want to make sure of 2 things. First, the carbon, in terms of our drawing, is going to shift either to the right or to the left. which is to say, if it was down here, it's now pointing up here. The other thing that you need to practice is being able to draw all of the hydrogens, both axial and equatorial, and recognize which one is which when you have a chair flip. Remember, something that was axial in one conformation will switch and become equatorial in the other flipped conformation.